Hello everyone, my name is Rubangakene Emmanuel Brady, and today I'll be connecting the core ideas of a diploma course from Alison to a real life project. The diploma course in question is a diploma in the fundamentals of AI, and I'll be connecting it to an AI powered restaurant air quality and safety rater. This AI tool restaurants rates the restaurants in Kampala on both their food and also their quality. And I mean, I beg your pardon, on both their food quality and also their air quality. But before we go any further, I would like to give you a small overview of the AI tool. This AI tool is called an air quality rate. Actually, it's an air quality rater called SafeBite. Think of it like a food safety rating, but not actually for food safety, but also for air. It combines it combines with sensors, beg your pardon, it combines data from sensors, uses users reviews and other sources to predict a safety score for the restaurants around Kampala. So the result is an application that shows you not just the best food, but also the healthiest place to eat from around Kampala. Well, on to the first module, which was AI history, trends, and future. AI's history shows a clear evolution, which started with symbolic AI, which focused mainly on logic and rules like expert machines. Then it shifted to a statistical approach to handle real-world uncertainties. And in today's world, AI is normally dominated by big data and deep learning. We have weak and strong AI. Um, Weak AI is basically tools designed for specific intelligence tasks without a conscious of their own. And then strong AI is majorly it's a theoretical concept of a machine which has a human-like conscious, but that is not the goal for today's project, because if you look at it, our project is a classic example of weak AI. Its tools are designed to solve one problem intelligently, but it does not have a conscious of its own. Integrating this with prior knowledge, the evolution mirrors data mining shifts from simple rules to complex predictive modules. To build it, we have to engage several of Gardner's intelligence types. For example, logical, mathematical for algorithms, naturalistic intelligence to interpret environmental data, and we also require interpersonal intelligence to understand crowd-sourced feedback. Philosophically, it sits firmly with the weak AI paradigm. Application of this project. Our AI quality rater situates itself within the modern trend of AI for social good. It doesn't just use a simple rule like if carbon dioxide is high, then the score is low. Instead, it uses machine learning. This is a machine learning, which is a current trend, to predict a score from noisy real-world data. This aligns perfectly with AI's trajectory towards handling complex and uncertain data. The second module was problem solving in AI, introduction to problem solving in AI, of which AI formalizes problems using three concepts: state, which is basically a snapshot of all relevant data at a given time; operators, actions that can change the state; and then a goal state, the desired outcome. This is the desired outcome these connect to data mining, as predicting a score is a type of search. It requires logical mathematical intelligence to structure. It also introduces frame problems. Then you ask yourself, how does the AI know which details in a state are relevant to air quality? We solve this by carefully selecting our features. Its application to the project. For us, the initial stage is our raw sensor and review data. The goal stage is a reliable safety score. The operators are functions in our code that process this data and run it through our machine learning module to find the solution. Well, this takes us to our third module, which is problem solving by search. There are two kinds of search algorithms, which is uninformed search, which is kind of, say, if I'm to use layman's word terms, I would say it's blind, because it is impractical for large continuous states, for a large continuous state space. But informed search is kind of smarter, I would say, because it uses a heuristic search, that is an educated guess, to guide it to the goal faster. In data mining, we use clustering to group similar restaurants to reduce complexity of the search space. This requires special intelligence. This requires social intelligence to use to navigate dimensional search space of environmental data and to display results on a map. We can also ask a philosophical question: Is our module prediction just a simulation of reality? And is it accurate enough to be trusted? Onto application of the project in this module. The training process of our machine learning module is informed search. The algorithm searches through millions of possible parameter combinations using mathematical heuristic to find the set that makes the most accurate predictions. This makes real-time scoring possible. Knowledge representation and reasoning is our fourth module. AI needs to store knowledge. First order logic is a very powerful way to do this with rules and relationships. For example, all restaurants with sensors provide live data. Well, data mining finds patterns like high traffic and closed windows lead to poor air, which can be turned into logical rules. This is an act of linguistic intelligence, but it has limits. You can can you really capture feelings like stuffness in a perfect logical rule? This is one of the reasons why we need machine learning. Application of this my project in this module, we can use a hybrid approach. This is a symbolic part that handles clear rules. If the sensor is offline, then use the prediction module, for example. Then the sub-symbolic machine learning module handles the messy subjective tasks of interpreting sensors and user reviews. This combines the precision of logic with the power of probability. As if you could read through the little information I've put above, you could see that I'm trying to explain exactly that. On to the fifth module, which is inference in first order logic. The FLO stands for first order logic. I just abbreviated it. It's not anywhere, but I hope you get that now because I've tried to talk about it. I've informed you. Inference. Deduction is deriving new facts known using rules. Beg your pardon. Deriving new facts, known facts, deriving new facts, known facts using rules. And soundness and completeness, ensuring inference are correct and the facts can be derived. So basically, inference is like drawing new conclusions from existing knowledge. From a rule and a fact, you can infer a new fact. The new output of our data mining module becomes a new fact for the system to use. This is pure logical mathematical reasoning. It also perfectly illustrates the Chinese room argument. The system manipulates symbols based on rules without any real understanding, which is a need for a weak AI tool. Its application in our project. Inference is used for decision making. If the inferred air quality is poor and the restaurant is tagged as family friendly, the system can infer a potential health risk for vulnerable groups and highlights it on the map. So basically what I'm trying to say is, let me just repeat what I've said, but I hope you try to get it. Our system uses inference for decision making, whereby if the air quality is going to be poor, but it is known as a family friendly restaurant, it can infer potential health risks for children and highlight it on the map, on the app. Pardon, I beg your pardon, on the app. This is considered as automated logical decision making. Well, on to the next module, which was reasoning under uncertainty, probability and Bayesian reasoning. Probability theory, essentially for handling incomplete and noisy data. Bayesian reasoning allows us to update the probability of hypotheses as new evidence arises. The real world is uncertain. Probability theory is how AI gets to handle incomplete and noisy data. Bayesian reasoning lets us update our beliefs as new evidence comes in. Integrating it with our prior knowledge, this is the core of data mining. Predicting probabilities. I beg your pardon. This is the core of data mining, predicting probabilities. Which is predicting probabilities. It requires naturalistic intelligence to handle ambiguous environmental signals. It also requires a philosophical admission. We can't always have certainty, but we can work with probability at times also. Where it's actually I it's as displayed on the board. How we apply that in my project, it is, could we read through this for a minute? It is crucial for us. Imagine if two users report stuffy and one says fine. Instead of getting confused, our system uses Bayesian reasoning to weigh the evidence and the probability of the air being bad. This is especially vital when we have no sensor data to rely and have to trust the word of the crowd. Yes, so it doesn't just doesn't just break and have nothing to say, or it doesn't just with the crowd feedback. It reasons and weighs the votes and tallies, and it goes with what the majority have to say. So if the majority say the air is bad, it will automatically say my AI system will automatically say the air is also bad because the majority say it's bad. It's just like a way of voting. On to my next module, which is planning. That's module 7. Planning is a sequence of actions to achieve a goal. In AI, systems like strips define actions by what must be true to use them. These are preconditions. And what they change are the effect. Those are effects. Integrating with the prior knowledge, we can use data mining to find action sequences that often lead to good outcomes, turning these sequences like body kinesthetics intelligence. The first problem reappears. How does the AI know what an action doesn't change? I would like to first give you that question to first think about. I'll give you the answer later on. But then again, it's just a question. It's a question that arises as the frame problem arises also. How do we apply this in our project? Our restaurant dashboard feature acts like a planning system. Its goal is to improve air quality. It generates a plan and an action. Like for example, action one will be recommending installing ventilation, and its precondition is there's a budget that will exist for it. Then the second action can be like suggesting adding of plants. Its effect, it's +5 to score. That's the precondition. These these sequences will be okay. The AI module will sequence these recommendations into a plan. Onto the next module, which is utility and I beg your pardon. Onto the next module, which is planning and decision making. Our subtopic is utility and decision making. Utility theory refers to assigning a value to outcomes to make optimal choices, and decision making refers to choosing actions that maximize expected utility, considering risks and constraints. To make the best decision, AI uses utility theory, assigning a value of each outcome. The best choice is the one that maximizes expected utility. Integrating this with prior knowledge, data mining provides the predictions needed to calculate utility. This requires interpersonal intelligence to balance the needs of users and restaurants. This is also AI's rationality. Beg your pardon. And this leads you to ask a question, a philosophical question. Is AI's rationality real? For a weak AI, if it works, it is. How we apply this in our AI tool. For a user, the app decides which restaurants to recommend by maximizing utility. So in simple terms, our app will not just show you restaurants, it makes decision for you. It calculates the utility score for each option, balancing food quality, air quality, and the distance. It then recommends the restaurant with the highest utility for you, making an optimal choice on your behalf. Well, this is our final module, which is machine learning. Um, Machine learning is basically how AI learns from data. There are two types of machine learning. There is supervised learning, which is our primary method. We train modules on labeled data to predict scores for new restaurants. And then there's unsupervised learning, which uses which clusters restaurants into types without any prior labels. Integrating this, data mining uses logical mathematics and naturalistic intelligence. It also makes us ask a question. Can our modules surpass human ability in predicting citywide air quality? In scale and speed, yes. In our project, we use we are majorly using supervised learning for the core prediction and uh, and the type of machine learning to analyze segments and to analyze the segments of customer reviews. This, in a sense, will turn words like stuffy, bad, noisy into data that makes our module smarter. Like I just mentioned, my project, the machine learning is an engine for our project. We I had actually explained this, but we use machine supervised learning to predict the air quality score from sensor data. But a really cool part is to use a type of machine learning called NLP. It's a branch of machine learning to read users' reviews. The module learns to spot words like stuffy, smoky, or fresh and uses that segment as a powerful signal to improve the predictions. I would like to thank you for going until the end of the video, and I would like to apologize again for the way I've had a rough voice, so I hope you got the message. Thank you and subscribe.